Hello, everyone, and welcome. Today, we're going beyond the typical list of trending AI tools. Instead of just showing you what's popular, I want to pull back the curtain on a professional's daily workflow, the specific stack I rely on to take a machine learning concept from a rough idea all the way to a robust, production-ready system. For the students and hobbyists here, you'll see how foundational concepts connect to real-world applications. For the data scientists and analysts, we'll dive into the tools that bridge the gap between insightful analysis and impactful models. And for my fellow ML engineers, we'll explore the architecture and MLOps principles that ensure our creations are scalable, reliable, and maintainable. This isn't about finding the one best tool. It's about building a cohesive, powerful toolkit and, more importantly, understanding the why behind each choice. Let's begin. Every project begins in the same place, the development environment. This is my digital workshop, where ideas are forged into prototypes. My primary tool is Visual Studio Code. It's more than just a text editor, it's a command center. With integrated Jupyter Notebook support, I can write and execute cells directly within my editor, keeping my exploratory code and production scripts in one place. This tight loop is critical for rapid iteration. For deep, narrative-driven exploration, I switch to a browser-based JupyterLab instance. Its flexible layout is unmatched for building a story with data, mixing markdown, code, and complex visualizations. Underpinning all of this is a strict versioning discipline. Git tracks every code change, which is standard. But for data scientists and ML engineers, the secret weapon is DVC, or Data Version Control. It works alongside Git to version large datasets and models without bloating the repository. Finally, everything runs inside Docker. Using containers ensures that my development environment is identical to my colleagues and, crucially, to the production environment. This practice eliminates the infamous "it works on my machine" problem before it even starts. This combination forms a reproducible, versioned, and isolated foundation for every project. Once a prototype shows promise, it's time to graduate from my local machine. This is where MLOps platforms become non-negotiable. My go-to for orchestrating complex workflows is Kubeflow. Running on Kubernetes, it allows me to define my entire training process as a portable, scalable pipeline. I can chain together components for data validation, feature engineering, distributed training, and model evaluation, all as code. This declarative approach is key for automation and reliability. Within this pipeline, MLflow serves as the project's laboratory notebook. Every single experiment is logged. The exact code version, the data hash, hyperparameters, performance metrics, and the resulting model artifact. This systematic tracking is the difference between ad hoc experimentation and a scientific, reproducible process. When a model is ready, MLflow's registry provides a central, versioned repository. For actual compute, I leverage cloud platforms like AWS SageMaker or Google's Vertex AI. They provide the on-demand GPUs and distributed training infrastructure that would be impractical to maintain in-house. Finally, for serving the model as an API, I rely on frameworks like SeldonCore or Kserve, which handle challenges like traffic splitting for A/B testing, canary deployments, and explainability right out of the box. This stack transforms a model from a file on a laptop into a scalable, enterprise-grade service. Pushing a model to production isn't the finish line, it's the starting line. A model's performance inevitably degrades in the real world, and our job is to catch it. This requires a two-pronged approach, monitoring and observability. For standard system monitoring, I use the classic combination of Prometheus for collecting time series metrics like latency, error rates, CPU, and memory usage, and Grafana to build intuitive dashboards to visualize them. This tells me if the service is healthy. But what about the model itself? That's where specialized observability tools are critical. I use libraries like Evidently AI to proactively detect silent failures like data drift and concept drift. Is the data coming into the model today significantly different from the data it was trained on? Is the relationship between features and the target variable changing over time? These tools automatically generate reports and visualizations that answer these questions. This is the core of observability, not just watching predefined dashboards, but having the tools to ask new, deep questions about your system's behavior when something unexpected happens. Without this layer, you are essentially flying blind. So, we've journeyed from intelligent content removal to instruction-based editing, and finally to efficient model personalization with Dreambooth and LoRA. The trajectory is clear. We're moving towards ever-increasing levels of control and specificity. The next frontier is about composing complex scenes and exerting granular control over the output. Technologies like ControlNet are leading this charge. By conditioning the diffusion process on additional inputs like depth maps, human-posed celatons, or canny edge detection, developers can now precisely dictate the composition and structure of a generated image. This bridges the gap between the unpredictability of a text prompt and the explicit control of traditional CGI. Looking ahead, these principles are being extended to generate coherent video sequences and 3D assets. What this means for us as practitioners is that these AI tools are becoming less like black boxes and more like programmable visual synthesizers, fundamental instruments for anyone building, designing, or working with intelligent systems.